Hello guys, welcome to our channel. I am Lara, and in this video we are going to talk about set covering problem, specifically about maximum covering location problem. Let's get started. Okay, so why do we need set covering? Imagine that a city wants to locate fire stations, ambulance centers, police stations, or emergency response units. The goal is not to minimize transportation costs directly. Instead, the goal is every customer or population zone must be reachable within a certain distance or time. If a demand point can be reached within the required distance, we say that it is covered. So what is the main logic of the set covering problem? We say what is the minimum number or minimum cost of facilities needed so that all demand points are covered. So what we find important in set covering problems, we have to cover as many nodes as possible. So what's the differences between transportation problems and set covering problems? So in transportation problem, the problem focuses on the flow or the cost, while in set covering problem, we focus on the coverage. In transportation problems, goods are shipped. In set covering problems, services are provided. Transportation problem, their demand allocations exist. In set covering problem, coverage requirement exists. In transportation problem, continuous variables exist. Set covering problem, mostly binary variables are used. Okay, so let's give some real life examples for set covering. So for ambulance locations, fire stations, police departments, libraries, hospitals, cell towers, set covering problems are used because the reason is simple. Every area must be reachable quickly. So each node, let's say, has to cover as much as it can. So what is a maximum covering location problem? So in set covering problem, we assume all demand nodes are covered. But in real life, budget may be limited, only a few facilities can be built, so full coverage may not be possible. So the main idea of maximum covering location model is instead of covering all demand, maximum covering tries to maximize the amount of covered demand using a fixed number of facilities. So what are real-life examples of maximum covering location model? A city may only afford 3 ambulance stations instead of 7 stations needed for full coverage. So the question becomes, which 3 locations cover the largest population? So let's look at the difference between set covering and maximum covering. In set covering, all demand nodes are covered, but in maximum covering, it only covers as much as it can. In set covering, it minimizes number cost of facilities. Maximum covering, fixed number of facilities exist. In set covering, full coverage is required, while in maximum covering, partial coverage is allowed. Okay. Here you can see the objective function and constraints of maximum covering location problem. So our objective is to maximize the demand covered as much as possible. And the constraint shows us here that if I do not open one facility, why should that facility cover any node? To make sure that any node that covers another node is opened, and if a facility is not opened, it does not cover any other facility, we use the first constraints. And then we have binary constraints of facility limit constraints. So it's basically that xj can only be 0 or 1 because or the facility is selected or it is not. And then we have the facility limits. So there are going to be facilities that can be opened. Let's say only 5 facilities can be opened, but we have 8 places. So we have to choose from those places. That's why we have the xj less than or equal to p constraint. Okay, so to understand the topic better, let's solve a question. It says a healthcare organization plans to improve emergency medical service coverage within a metropolitan area. Due to budget limitations, the organization can open only a limited number of emergency response facilities. The network represents candidate facility location, demand regions, and possible coverage connections between them. Each line indicates that the facility can cover a specific demand node within the required service distances. The organization can open at most 2 facilities. Coverage distance is at most 15 units. Okay. So I have a network ready. At the network, you can see each demand for each node and the distances between nodes. So as you can see, not every node can go to every node. I've already prepared the IJ and AIJ matrices, but let's look at what they actually mean. So the IJ matrix is the distance between a node from a node to another node. So from node A to E, it's 14 units of distance. From C to E, it's 7 units of distance, and etc. So, but let's look at it and how I did it. From A to D, as we can see, it's 8 units of distance, and I've already written that there. From A to E, it's 14 units of distance, and I've already written that also. But from A to F, we have more than one ways. So how have I chosen? So from A to D to F is 8 plus 10, so 18 units of distance, 18. And from A to E to F, it's 19 units of distance. So what I did, if there is a way that, if there are more than one ways to go from one node to another node, I chose the minimum distance because that's what we're trying to do, minimize distance so we can cover the most nodes, demand. Okay, so then I have written all the distances. You can compute it yourself, you can check it yourself, and please do it to learn it. Okay, so our next step is going to be AIJ matrix, but what is that? So as you can see in the question, it says the distance, coverage distance is at most 15 units. You have to disqualify the distances if it is more than 15. So let's look at our DIJ matrix. Yeah, so A to D, it's 8 units of distance, less than 15, I can get that. From A to E, it's 14 units of distance, again, less than 15, I can include that. But from A to F, it's 18 units of distance. So as you can see here, in the AIJ matrix, A to F, I have given it a 0 because I cannot cover that because it's more than 15. Same for G and H, 22, 17, more than 15, so I cannot cover it. Let's look a few more. From B to A, as I can see here from the network diagram, I can't go from A to B. Because I can't go from A to B, I have written a stripe there, and that stripe translates to AIJ matrix as again a 0 because I cannot go there. So why should I give it a 1? Okay, so let's just look at one randomly. CD from node C to D, it's less than 13. So I can include this as 1 because it's less than 15. So if we have understood the IJ matrix, we can start to write our constraints and objective function. Objective function. So what is our objective in this question? We have to maximize the demand that is covered. So maximize, what are we going to maximize? Demand covered. Okay, so I'm going to write this in the open form. Let's look. So node A has a demand of 35. 35. I'm going to multiply this because I have to go. I have to think: is this covered or not? If it is covered, the demand 35 is going to be covered as well. So I'm going to write ZA plus 50 ZB plus 40 ZC. So I'm going to multiply all the demands with the binary variable in which if it is going to be covered or not. And then 55D, 55ZD plus 25ZE plus 30ZF plus 40ZG plus 25ZH. So this is going to be our objective function. So let's look at our constraints. So subjected to, so we have to now write a constraint about if I open a facility, that facility can cover the other nodes. If I don't open that facility, I have to make sure that it does not seem to cover other nodes. Okay, so start with our constraints. We have to know what these ones mean. So if you look at this row, okay, to be able to cover node A, these nodes that have 1 in them has to be opened. So to cover A, node A should be opened. A facility at node A should be opened, or a facility at node D should be opened, or a facility at node E should be opened. So we say if a facility at node A, D, or E should be opened, that means node A is covered. So one of these should be opened to be able to cover node A. So that's what we are going to do for all these nodes. So for B, to be able to cover node B, or node B itself should be opened, or node D should be opened, or E, or F, or H. So XB plus XD plus XE plus XF plus XH, one of these should be opened so that VB can also be opened. So this means if this is 0, this can never be 1. You know, it always has to be 0, so it can't be covered. So if you go for C, to be able to cover node C, C, D, E, F, or G should be, a facility at those nodes should be opened. So XC plus XD plus XE plus XF plus XJ, one of these should be opened to be able to open, to be able to cover node C. Okay, so for D, A can be opened, B, C, D, F, J, and H, basically everything but node E can cover node D. So it should be less than, more than or equal to Z D. Yes. Okay, so let's do for the other ones. So for E, XA plus XB plus XC plus XE plus XF plus XJ plus XH, and that should be more than or equal to ZE. Yes. Okay, and then for F, XB plus XC plus XD plus XE plus XF, and this should be more than or equal to ZF. And then for G, XC plus XD plus XE plus XG, and this should be more than or equal to ZG. And the last one for H, XB plus XD plus XE plus XH should be more than or equal to ZH, so that we can cover the node H. So we need one more constraint, and that is for the facility capacity constraints. We have 2 that we can open. So we are going to say, so XA plus XB plus XC plus XD plus XF plus XE, J, and H. And that should be less than or equal to 2 because we cannot open more than 2. And as the last constraints are binary constraints, of course, ZI, which is from A to H, it has to be 1 or 0. And for X, the same. So Xi can be 0 or 1 because it's a binary variable. Okay, so thank you for watching our video. If you're curious, if you have learned a lot in this video, please scan this QR code to test yourself, and I'll see you in our next video.